So, well, thanks for the invitation. So I'm really happy to be here. So I counted that's my fifth time in.
Fifth time.
Yes, in the John.
Yeah, I enjoy.
And I also enjoy a lot. Yeah, being here. So the talk will be very elementary. So I apologize for those of you who know already these things, and. So it's somehow meant to be a preparation for Eduardo's talk that comes after.
Actually, my talk will be exercises of your talk.
Okay. Okay, and let me start with some setup and notation. So K will be an algebraically closed field. And to avoid questions about the characteristic, I'm going to assume from the start that it's of characteristic 0. Well, this hypothesis is not necessary, but just to keep things as simple as possible. So we take V a vector space of dimension n plus 1. Usually we take x0, xn a basis. And S is the symmetric algebra of V, which is, so I'm going to use this notation Sn. Sn is the vector space of homogeneous polynomials of degree n. So this is, of course, isomorphic to the polynomial algebra in x0, xn. And the question that we ask, if M is a graded, finally generated S module, what prevents M from being a free module? So, of course, if we don't have any variables at all, so if we just work with for vector spaces, if we take one EM minimal set of generators, then this is linearly independent, and this gives this gives freeness. But for modules in general, that's no longer true. And since this is finally generated, we can always talk about a minimal system of generators. So what makes the difference between vector spaces and modules is this linear independence. And if we take just one example, take P a point in P2, take IP the homogeneous ideal. This is, so N is 2 in this case. Well, this homogeneous ideal is generated by a linear force because the point is the intersection of two lines. This is a minimal system of generators because we cannot, so if we take just one generator, then we get a curve. We don't get a point anymore. And this is not free. IP is not free. It's not free because these two are not linearly independent. We have a, so L1, L2 are not linearly independent. I should write linearly in quotes, linearly independent, because we have this trivial relation L1, L2 minus L2, L1 equals 0. So that shows that this is not a free module. So essentially, what prevents, so to answer this question is so what prevents, so answer to the question is the existence of relations so the existence of relations among the generators in a minimal system. In a minimal generating system. That's what makes the difference between free and non-free. So this is how we come to syzygies. So these relations are actually syzygies. So let's discuss a little bit more what is a syzygy. So what is a syzygy? Syzygy. So let's assume we come back to the original situation. We have M, a finally generated graded module. We take y1, yn, a minimal system of generators of M. Okay. And if M is not free, then we have a relation. So there exists a relation of the following type. So sum I from 1 to n, pi yi, where pi are homogeneous polynomials. So since this is everything is graded, this is y1 or yn are can be taken to be homogeneous.
And equal to 0.
Equal to, yes, thank you. Equal to 0. Okay. So we have a syzygy. So a syzygy is basically a relation like that. So but what does it mean to have a syzygy? So in other words, we have in other words we have a morphism. Just I forget about the grading for the moment. I just take like usual elements. So if I take the morphism phi from Sn to M, mapping the elements of the canonical basis in Sn to these y, which are the elements of the generating system of M. So E1, En is the canonical basis. Then a syzygy is an element of the kernel of phi. So we can see it either as an element of the kernel of phi or a column P1 Pm in S to the n. Well, it has to be a column with the sum of pi y I equals 0. So in general, a syzygy will be seen as a column vector. Okay. And now, so this is that's what a syzygy is a column vector that multiplied with, so we can write sum of pi y equals 0 as if we multiply y1, yn by the column p1, pn, this is 0. Now the kernel of a map is a submodule of S to the n, and since S is a Noetherian ring, this is also finitely generated. So we can continue, we can iterate the procedure. So kernel of phi is finitely generated, graded S module, so we can continue. And continuing, we obtain what's called a minimal resolution. So I'm going to give the definition first. So a minimal resolution of M is an exact complex of graded S modules, and I write it like that. So F0, F1, Fi, and so on, Fn plus 1. So the fact that we can always stop at n plus 1, so there is no mistake here, it's the same n. So the fact that we can stop here is ensured by the Hilbert syzygy theorem. Where these Fi's are free, which means that we can write, so Fi is the direct sum of S minus j to beta ij over j. And for some reasons that I will explain a bit later, I will use the following notation. So k, little kij, or in other, in some papers you find the notation bij. So kij is beta I plus j. Okay, so if we use this notation, then we can also write Fi to be the direct sum of S minus I minus j to the kij over j. So it's the same. It's exactly the same thing. Okay. So graded means that all the differentials here in this complex are in degree 0. And now minimal means one of the following three equivalent conditions. So one of the following equivalent conditions are satisfied. So the first one is that the matrices associated to these differentials, so let's put some names here, di, so that would be d1, that would be dn plus 1, associated to di do not have non-zero constant entries. So these modules are free modules, so these are maps between the free modules, so they are represented by some matrices. Since everything is graded, the entries of these matrices are homogeneous polynomials, and the requirement is that among those polynomials they are also either 0 or of degree at least 1. So we have no constant non-zero entries in these matrices. Or the second is that the rank of Fi is the minimal number of generating set of the kernel of vi minus 1. Or the third one is that when tensored by the residual field k, which is S over the ideal generated by the variables, the differentials become 0. Yeah, because twisting by the residual field means that we evaluate all these polynomials in 0. Okay, and some remarks. The minimal resolution is unique up to isomorphism. So it's not unique in the sense that we can change these matrices. We can have different matrices, but these terms are unique. So in particular, the numbers beta ij only depend on m and are called degraded Betti numbers. Of the module M. So these are some fine invariants of this module. Okay, and they coincide. So another remark is that beta ij is the dimension of Tor I S M K J, right? Because K is this residual field. When we tensor by the minimal resolution by the residual field, we kill all the differentials, and here we obtain vector spaces whose dimensions we compute. So these are essentially these Betti numbers. And usually to keep track of them, so to keep track of them, we organize them in a table called the Betti table, like that. So we put here the numbers Kij. So that would be on so j is constant on rows and I is constant on columns. So the j's go like that, and the i's go like that downwards. So that's the orientation of the table. So in particular, we will have Kij, then Ki plus 1j, Ki minus 1j, Kij plus 1, Kij plus 2, and so on. So that's the structure of the Betti table. Or if we can replace this Kij by beta I plus j, and then we get beta I plus j. Here we have beta I plus 1, I plus j plus 1. Here we have beta I plus j plus 1, beta I plus j plus 2. Here we have beta I plus 1, I plus j plus 2, and so on. So in this new notation, the second index is constant on diagonals and not on rows, as before. Okay, so let's give one example. I should have mentioned that the syzygies, since the syzygies, so I should mark this here, that syzygies are columns of the matrices associated to di's. So if we want to keep track of all the syzygies, we better look at these matrices, and the columns will be the corresponding syzygies. And let me give a very simple example. So X is 3 points, a collection of 3 points P1, P2, P3, 3 distinct points in P2. And we are interested in, N is 2 in this case. We are interested in the homogeneous coordinate ring of this set of points. And we have two cases. So the first case is when P1, P2, P3 are not collinear. And of course the second case is when these are on a line. Okay, so in the first case, so up to a projective transformation, we can assume that P1, P2, P3 are the coordinate points. Because for any 3 points not on a line, we find a projective transformation that sends these points to the coordinate points. And then if we want to cut out these points by equations, well, we can, since they are not on a line, we cannot use linear equations, but we can certainly use quadratic equations. So we have the first quadric is the union of these 2 lines. Then a second quadric would be the union of these 2 lines. So the intersection of the 2 quadrics is this point and this line, which is common to them. And if we want to rule out, to exclude this line, we better take the third quadric, which is union of these two lines. And then the intersection of these three quadrics is exactly this set of points. Well, of course, we cannot describe these 3 points just by two quadrics, because the intersection of two quadrics is by Bezout 4 points. So these points, these quadrics will give a minimal generating set. So Ix is generated by Q0, which is x1, x2, Q1, x0, x2, Q2, which is x0, x1, and Q0, Q1, Q2 form a minimal generating set for the ideal. And now, if we want to build the minimal resolution, so Sx has one generator, which is 1. Then the kernel is the ideal, so now we have to take a minimal set of generators. And we have 3, so we have S to the 3, and here we have Q0, Q1, Q2, but we want to make it a morphism of graded modules, so we have to shift by 2, because these are of degree 2, so we want the differential to be in degree 0, otherwise the differential would be in degree 2, and that's not what we want. And now we have to continue with the kernel of this map, so we have to know the relations among Q0, Q1, Q2. But there are some obvious relations, like if we multiply this by x0, we get x0, x1, x2, if we, which is the same as this one multiplied by x1 or this one multiplied by x2. So the relations are x0, Q0 equals x1, Q1, x2, Q2, which gives two linear relations. Which are x0, Q0 minus x1, Q1 equals 0, and the other one is x0, Q0 minus x2, Q2 equals 0. Of course, the last one is just obtained by subtracting these two relations. So if we add the third one, it depends on these two relations. And we said that each time we have a relation like that, so we have a syzygy, we take the coefficients and organize the coefficients in a column. So we will get a matrix like x0 minus x1, 0, and the other one would be x0, 0 minus x2. And this matrix gives us x0, x0 minus x1, 0, 0 minus x2. The end of the resolution. So that's how we build the resolution, and that's what we do in general, just that in general the situation will be, of course, much more complicated. And the second case is slightly simpler. So in case 2, we have the 3 points on a line, and if we want to describe the ideal, so we have a cubic that passes through these 3 points, and the ideal will be generated by this linear form that defines the line and the equation of the cubic. So and then the beginning of the resolution looks like that. So we have LR. Here we have S minus 1 plus S minus 3. And then between L and R we have one relation, which is the trivial relation, L times R equals minus R times L equals 0. And if we put this on a column, so we get R minus L, and we have S minus 4 here. So that's the minimal resolution in the second case. Okay, so that was one example. So in general, the computation of the minimal resolutions is not as easy. So it's a very complicated task. And but anyway, before going further, I would like just to. I should hurry up a little bit. I should speak about the relations with the Hilbert function. So I go back to the original situation. So M, a finally generated graded S module. And then from the exact sequence, so from the exact sequence in degree n, so we have Mn, F0, n, F1, n, and so on, where F was the minimal resolution of M. So this is an exact sequence of vector spaces. We get Hm of n, which is the degree of this vector space, is the sum minus 1 to the I, beta ij, and here we have n plus n plus n minus j, choose n. So these graded Betti numbers are finer than the Hilbert function, because the Hilbert function can be recovered from the graded Betti numbers. So these beta ij are finer than the Hilbert function. What about the converse? So the converse in general is not true. So the Hilbert, the Betti numbers cannot be recovered from the Betti numbers. There are examples. If you take, so in general, the Hilbert, the Betti numbers cannot be recovered from the Hilbert function. So they are sort of strictly finer than the Hilbert function. And one example, but I'm not going to discuss because I will run out of time. Example, you take 4 points in P2. So if you take 4 points which are not on a line, or 3 on a line and 1 off the line, the Hilbert function of these configurations of points are the same, but the Betti numbers are not the same. So in this case, the first case, the Betti table looks like that, and in the second case we have 1, 1, 1, 1, 1. So there is a slight difference between the two. Sorry, that's not 1, it's 2. Between the two cases. Okay. However, what we remark is that. So that's a very stupid remark. They are all almost the same, except that we put a 1 here and here instead of zeros that appear here and here. But 1 minus 1 equals 0. And the question is this a general fact? So does it mean that if we have 1 minus 1 is 0 and we have 0 and 0 here, does this mean something? And it does. So there is some, however, there is some relation between the alternating sums on the diagonals of the Betti numbers and the Hilbert function, and that comes from the easy observation that if we take n to be, let's see, to be maximum here in this sum, so that sum runs over I and j. This coefficient will become 1. So what I'm trying to say is the following. So let me add some more notation. So let's denote by capital B j to be this alternating sum of minus 1 to the I beta I j. So that is the sum taken over I. So with this notation, hm of n will become a sum of bj n plus n minus j choose n. So that's the sum over j. And now in this case, if we take j to be n, so in this sum we will have one coefficient which is 1. And for that coefficient we can compute it in terms of the others and the Hilbert function. So what we actually get is that bj is in fact hm of j minus a sum over k lower than j bk n plus n minus k choose n. So what does it mean in terms of
I mean bn.
Yes, bn, yes, thank you, bn n. What does it mean in terms of the Betti table? It means the following. So, for the Betti table, the bj's are, so we take the diagonal, and bj is computed by the alternating sum of the elements on this diagonal. So for example, it's the alternating sum here. So that would be b0. This one minus this one will be b1. Sorry, minus this one will be b1. This one minus this one plus this one will be b2. This minus this plus minus will be b3, and so on. So the alternating sum of the elements on the diagonal is bj. And if we compute them up to the step bj minus 1, then this capital Bj can be deduced from the others and the Hilbert function. Or Bn in this notation. Bn, let's call it Bn. So the moral is that the numbers that appear here, which are the graded Betti numbers, are not determined by the Hilbert function. However, their alternating sum is determined by the Hilbert function. Okay. And now we have this Betti table, and now the question is, So the question is, what do we read of a Betti table? And to keep the things simple, let's assume M is Sx, where X in Pn is a projective variety. Let's also assume that it's non-degenerate. Although that's not necessary. So then the Betti table will look like that. So we will have a 1 here, which corresponds to... So remember that on each column, we read the... so on column I, we read the generators of the module Fi. So on column I, we have the generators of Fi, the degrees of the generators of Fi. So F0 for a coordinate ring is always S. So we have a 1 which corresponds to S. And then here we would have 0 because on so that's the first column only has one generator in degree 0, so that we read it here. On the second column we read the degrees of the generators of F1. But what was F1? So F0 is F, S goes to Sx, goes to 0. And now F1, we'll keep track of the generators of the kernel of this map, but the kernel of this map is the ideal. So F1 keeps track of the generators of the ideal. So on the next column, we read the generators, the degrees of the generators of the ideal, Ix. So for example, here we have the number of quadrics. Here we have the number of cubics, and so on. We have quartics, and so on. And then we move to the next one. On the next column, we have we go one more step. So we read the degrees of the generators of F2. But what are the generators of F2? So they give the elements of the kernel of this map. So this means that on this column we read the degrees of the relations among the generators of the ideals, of the ideal. So here we read the degree of linear relations among the quadrics. Here we have relations which are linear with respect to the quadrics and quadratic with respect to the quadrics and linear with respect to the cubics. So here we have degrees of relations which are quadratic with respect to quadrics and linear with respect to cubics, and so on. On the next column, if we move on, this means that we move on one step further in the resolution, and then we read the relations among the relations, and so on. And the main goal of the syzygy theory is to understand these Betti tables, the meaning of these Betti tables. So the main goal is to understand the connections between the Betti tables of either Sx, which are coordinate rings, or Sx twiddle, which are the integral closures of coordinate rings. So to understand the connections between these Betti tables and geometry, the geometry of X. Okay, and there are some. May I go a couple of minutes over time?
Yes, so 47.
Okay. So we need, since computing, so a remark, computing graded Betti numbers is difficult in general, so we need methods to compute them, and I will list here some known methods. So the first one, which I will discuss in the last minutes, is using Koszul cohomology. Then kernel bundles. So these are kernels of evaluation maps. And then another option would be to use the Grassmannian, the geometry of G1 Pn. So the geometry of the Grassmannian of lines in Pn, especially when we compute KP1s. And finally, that's due to Vazin, is to use Hilbert schemes. And one more method is to use Koszul modules, and that's what I've done with Farkas, Papadima, Raiku, and Weimann, to use Koszul modules. But I'm afraid I don't have time to explain the relation with Koszul modules, so I will stick to Koszul cohomology. So what is Koszul cohomology of M? So this is KPQ of M is the cohomology at the middle of the complex. So that's a vector space, I should say. So that's a complex of vector spaces. So wedge P of V. So V was the original vector space whose symmetric algebra we considered, tensor MQ. Then it comes from wedge P plus 1 V tensor MQ minus 1. We also wedge P minus 1 V tensor MQ plus 1. So remark that the sum of the indices here is the same, and these are delta. So this is delta P. So delta P acts as follows: delta P of xi 1 wedge xi p tensor an element y is the sum minus 1 to the j xi1. We remove what's on the position j xi p, and we add xij multiplying by y. So now we see why why is the codomain is the right one, because here we reduce the number of the elements of the multi-index, and we increase the degree on n. And an important fact, what's this good for? So the fact is that KPQ is the dimension of KPQ of M. So the graded Betti numbers are actually dimensions of this this Koszul cohomology, and one important remark. If we work with if we work with M, which is Sx, we denote, so we look at KPQ of Sx. Well, this is isomorphic to Kp minus 1 Q plus 1 of Ix, because we have a short exact sequence of graded S modules, which is Ix goes to S, goes to Sx, goes to 0. And these KPQs are graded Betti numbers, so they are dimensions of torus. So for each short exact sequence, we have a long exact sequence of torus, and we use the fact that, so use the tor long exact sequence plus the fact that KPQ of S is 0 except for PQ is 0, 0. So in particular, if we look at KP1, so KP1 of Sx is Kp minus 1, 2 of Ix. But Kp minus 1, 2 of Ix, if we look here, what does it mean? So Kp minus 1, 2 of Ix would be Kp, so it's computed starting from HP of V tensor IQ1, Ix1. Ix1 contains the linear forms in the ideal, and since X is non-degenerate, this is 0. So roughly speaking, this is the kernel. This is just the kernel of the map delta 2 that goes from wedge P minus 1V tensor Ix2. So these are the quadrics in the ideal. And here we have delta 2, which goes to wedge P minus 2 of V tensor Ix3. These are the cubics. So it's a sort of, so we just plug in the Koszul differential, and we have the kernel. So the moral is that, at least when we look at KP1s, what is KP1? So KP1 is actually a collection of quadrics. So for any P so for all, in particular, for all P Kp1 of Sx, so any element in Kp1 is a collection of quadrics containing X. And these Kp1s are really interesting in view of the interactions with the geometry. So Kp1s are important. So the KP1s, the K11 gives the quadrics in the ideal. The K21 gives the relations among the quadrics, linear relations among the quadrics. Then K31 is the linear relations among the linear relations, and so on. So it's called the linear strand of the resolution. So they are important in syzygy theory. And somehow the driving problem in regarding the KP1s is Green's conjecture, saying that if x in Pg minus 1 is a canonical curve, then we can read off the Clifford index of x, which is an important invariant of the curve, from the KP1s. Okay, and I think I will stop here. Thank you.
Thank you very much.